Welcome to Institute of Quality and Reliability. Hi, this is Hemant.
Introduction to Measurement Systems Analysis. In this video, we will explain briefly the terminology used in measurement systems analysis, which include accuracy, precision, bias, linearity, repeatability, reproducibility, and stability. We will then explain the relationship between measurement and process variation using the concept of additivity of variances. We will later explain and illustrate the procedure for repeatability and reproducibility study. We will then explain the acceptance criteria for the study variation and the variance components method. Finally, we will explain the analysis and interpretation of the results using SigmaXL software. Let us understand what is accuracy. If we measure the same part number of times, we can take average of the measurements. Closeness of agreement between this average and the true value is the accuracy. Accuracy is usually quantified in terms of bias. If we measure the same part number of times, we can take average of the measurements. Difference between this and the true value is bias. Bias is a systematic error component of the measurement system. Calibration helps minimizing the bias during usage of the instrument. Let us understand the term linearity also. Linearity is the change in bias over the operating range. It is again systematic error component of the measurement system. And stability is the change in bias over time. But then what is precision? Precision is closeness of repeated readings to each other. It can be considered as random portion of the measurement error. We can understand the difference between accuracy and precision with the following three figures. Figure 1 shows accurate but not precise. Figure 2 shows precise but not accurate. And figure 3 shows accurate and precise. Now let us understand the term repeatability. If the same operator measures same part number of times, the closeness is a measure of repeatability. Traditionally, it is referred to as within appraiser variation in the repeatability and reproducibility study. It is also known as equipment variation, short form E.V or EV. So what is reproducibility? Reproducibility is variation in the average of measurements made by different appraisers or operators using the same measuring instrument when measuring identical characteristic on same part. Reproducibility has been traditionally referred to as between appraiser variation or appraiser variation AV. Let us understand the relationship between measurement and process variation. The process variation and measurement variation is seen as observed total variation when we perform measurements on parts. Based on the property of additivity of variances, this relationship can be mathematically expressed as sigma total sigma t equals square root of sigma p square plus sigma m square, where sigma p is the process standard deviation and sigma m is the measurement system standard deviation. Generally, the bias, linearity and stability study of measuring equipment is done separately. In this video, we will briefly explain the procedure for repeatability and reproducibility study, commonly referred as R&R study. In the R&R study, the variation due to repeatability and reproducibility is separated by performing an experiment. Based on the property of additivity of variances, this relationship can also be expressed mathematically as sigma m is equal to square root of sigma AV square plus sigma EV square, where sigma m is the measurement standard deviation Sigma AV is the standard deviation of reproducibility and sigma EV is the standard deviation of repeatability. Ideally, we do not want any measurement variation. However, this is not possible in reality. Therefore, we need to ensure that measurement variation is a very small portion of the observed variation. Let us now understand how to calculate gauge repeatability and reproducibility, that is GRR. As discussed earlier, if sigma p is the process standard deviation and sigma m is the measurement system standard deviation, then the standard deviation of the total variation sigma t will be given by square root of sigma p square plus sigma m square. The ratio of standard deviation sigma m upon sigma t is called gauge repeatability and reproducibility, that is GRR. It is usually expressed as a percentage value. GRR should be less than 10%. Percent GRR is equal to sigma m upon sigma t into 100, and the values of sigma m and sigma t are estimated using the GRR study. Let us now understand a procedure for performing gauge repeatability and reproducibility study. First, decide the part and the measuring equipment that you want to use. Establish and document measurement method. Train the appraisers or operators for the measurement of the particular characteristic that you have decided. Select 2 or preferably 3 operators to perform the study. Select 5 to 10 parts, preferably 10 parts. The parts selected should represent the process variation. Each part must be measured by each appraiser at least twice, but preferably thrice. Measurements must be taken in random order so that each measurement can be considered as independent. The appraiser who is taking any measurement should not remember what he has or she has measured last time. Record, analyze, and interpret the results. There are two methods for analysis of gauge R&R study. First method is control chart method, which is simple to use and understand. And second method is ANOVA method or analysis of variance method. This requires understanding of ANOVA, its interpretation, but shows operator part interaction as well. The Automotive Industry Action Group MSA manual recommends ANOVA method as preferred. And with modern softwares, it is easy to perform analysis using both the methods. We will use the ANOVA method. Consider that we decide to measure internal diameter of a gear using a dial bore gauge. As per the procedure for performing the gauge R&R study, we select 10 gears randomly and select 3 appraisers who are trained to measure using a dial bore gauge for measurement of the internal diameter of the gear. There is a note. Such a study, when each appraiser measures each part, is called crossed gauge R&R study. If the parts get deformed or destroyed or the measurement system gets destroyed during measurement, such a cross study is not possible. In the R&R study, measurements must be performed in random order and appraiser should not know which part he or she is measuring. This is necessary to ensure that each measurement is independent and unbiased. Here is the layout for gauge R&R study with 10 parts and 3 appraisers. The variation within each 3 measurements of the same part by the same appraiser are estimates of repeatability. The difference between average measurement of each part by the 3 appraisers are estimates of reproducibility, and The variation in the average of 9 measurements of 10 parts is an estimate of the process variation. Let us now see an application example of a gauge R&R study, and we will use SigmaXL software for this. We will consider the example of measurement of internal diameter of a gear using a dial bore gauge. The tolerance for the bore size is 9.950 to 10.050 millimeters. We can use a template of gauge R&R study provided in SigmaXL software. SigmaXL has many such useful templates. After entering the data of the GRR study, the template looks like this. Similar template is also available from the downloads section of our website www.world-class-quality.com. Note, the trial version of SigmaXL software can be downloaded from their website www.sigmaxl.com. After you download and install SigmaXL software, you will see two additional menu commands in Excel when you open a blank file. The first command is SigmaXL. So you will see a ribbon that looks like this, and the other one is chart tools. We will use the SigmaXL ribbon commands, and we will only use the measurement systems analysis. But just to make you familiar with the other commands, it includes data manipulation, templates and calculators, graphical tools, statistical tools, measurement systems analysis, process capability, design of experiments, control charts, reliability variable analysis, and time series forecasting. So we will start with measurement systems analysis. Now you can create a gauge R&R crossed worksheet. If you click here, it will allow you to create a worksheet when you can enter how many parts, how many appraisers, and how many replicates or trials. We will use template instead of this. So I go to measurement systems analysis and basic MSA templates and go to gauge R&R study measurement systems analysis. So this creates a blank worksheet in the template. Here we are supposed to enter the data of the 10 readings by operator A, in the next 3 rows by operator B, and in the last 3 rows operator C. And here you can put the name of the gauge, who has conducted study, when, etc., notes. And here you can put the tolerances, upper specification limit and lower specification limit. Alternately, you can also put only the process tolerance. Now let us see the worksheet where the data is already filled in. So I go to the gauge R&R, and now this is the dial bore gauge as the gauge name, 28 February HPU, example for illustration. The upper specification limit is 10.05, lower specification limit is 9.95. Standard deviation multiplier is 6.0, which is the default multiplier. And now the operator A readings are entered here. Operator B readings are entered in the next 3 yellow colored rows. And the last 3 rows are readings by operator C for the 10 parts. If you scroll down in the template, you will see that SigmaXL has already performed complete analysis of the data, and you will see a table of the complete analysis. Let us interpret this table. The first column shows gauge R&R metrics. The second column is variance components and percent contribution of variance components. This is variance or not standard deviation. The next column shows the values of standard deviation. So this row, for example, is a standard deviation of the gauge R&R that includes appraiser variation AV here 0.004566, and operator part interaction. Now it also calculates using the ANOVA method, but it's 0 in this particular case. And reproducibility is, so since this is 0, the total reproducibility is 0.004566. The repeatability EV is 0.004288, and as a sum total of these two, the gauge RNR is 0.006264. So 0.006264 is square root of addition of the squares of reproducibility value and repeatability value. So 0.004566 square plus 0.004288 square and square root of the sum. The next column is standard deviation multiplier. Now important column for our first understanding is percent total variation, and this is 28.75. We will look at the norms, and percent tolerance is also included in the last column. Now let us do a complete interpretation of this table. Let us now understand the calculations of gauge repeatability and reproducibility. Recall that the standard deviation of the total variation sigma t equals square root of sigma p square plus sigma m square, where sigma p is the process standard deviation and sigma m is the measurement system standard deviation. And the ratio of standard deviations sigma m upon sigma t is called the gauge repeatability and reproducibility. It is usually expressed as a percentage. Let us now understand the acceptance criteria for the gauge repeatability and reproducibility. In the study variation method, the gauge repeatability and reproducibility of 10% is considered acceptable so that the GRR ratio sigma m upon sigma t is less than or equal to 0.1 or 10%. In the variance components percent contribution method, the ratio is squared and therefore the acceptance norm will be 0.1 square or 0.01, that is 1%. The following table summarizes the criteria in the study variation and percent contribution method. So the first row of the table shows the acceptance criteria in the study variation as 10% and acceptance criteria as 1% for the percent contribution method. Thus, the gauge is acceptable if the GRR is less than or equal to 10% or percent contribution is less than or equal to 1%. When the ratio of sigma m upon sigma t under the study variation method is between 0.1 to 0.3 or 10 to 30%, it will correspond to squared ratio of 0.01 to 0.09 or 1 to 9% in the percent contribution method, and the decision in this case will be gauge is conditionally acceptable and generally customers approval is expected in this case. Finally, when the ratio of sigma m upon sigma t under the study variation method exceeds 0.3 or 30%, it will correspond to ratio of variances of 0.09 or 9% or more, and under this condition the decision will be gauge is unacceptable. If we apply these criteria, the gauge is conditionally acceptable for this measurement application as the GRR is 28.75 under study variation method and 8.27% under percent contribution method. Also, the appraiser variation AV as well as the equipment variation EV both are nearly 20%. Continuing with the interpretation of results, the last column of the table shows percent tolerance, which is usually referred as P by T ratio. The value of this is shown as 37.59% in the table. The P by T ratio equals 6 times sigma m upon tolerance, and that is equal to 6 into 0.00626 divided by 100, which was the tolerance, and that equals 37.58%. The acceptance criteria for the P by T ratio is same as that for study variation method, and therefore the gauge is unacceptable for P by T ratio. When the P by T ratio exceeds 30%, that means the gauge is incapable of distinguishing between good and bad parts based on the tolerance. We can perform more detailed analysis in SigmaXL by creating another worksheet using the command create stacked column format for analyze gauge RNR. So I click on this command. SigmaXL has created another worksheet that offers more capabilities of analysis. You can see that the original template worksheet has been converted into a column format, stacked format, but there are 90 rows and it is the same data which is seen in different format. We can now perform more detailed analysis using this new worksheet. For this, I use the SigmaXL commands for measurement systems analysis, analyze gauge R&R across, use entire data table. In the part, I select the part column. In the operator, I select the operator column. In the measurement, I select the measurement column. The standard deviation multiplier is 6, which is the default value. We can change it to 5.15, but 6 is recommended in the automotive industry action group. Alpha to remove interaction is default value is 0.1, which is 10% alpha risk. Confidence level is 90%. Finally, I add the tolerance of upper minus lower specification as 0.100 and I click OK. Most of the results will be same as before in the template, and here you can see that the percent tolerance is also 36 point. It's a small difference in the calculation. The template and these readings are very slight difference between the two readings. There is one additional information that it has given, the number of distinct categories as 4.9. The number of distinct categories should be at least 5 and preferably more. So 4.9 is less than what is acceptable. So in that sense, this gauge is not acceptable for the NDC. Also, in addition to the template, it shows the analysis of variance tables. So these tables show the analysis of variance. But remember, this ANOVA uses the random effects models instead of the fixed effect model. Let us do a quick recap. In this video, we have briefly explained the terminology used in measurement systems, which included accuracy, precision, bias, linearity, repeatability, reproducibility, and stability. We have discussed the relationship between measurement and process variation using concept of additivity of variances. We have explained and illustrated the procedure for repeatability and reproducibility study using SigmaXL software template. We have then illustrated how to use the template for analysis of the data and interpretation of the results. We have finally discussed the acceptance criteria for the study variation and variance components method. Thanks for watching this video. Hope you found it worth watching. Please subscribe to Institute of Quality and Reliability channel if you want to watch more videos on reliability engineering, Six Sigma and quality engineering.